Okay, this is section 2.4. We're going to talk about compound interest now. So from section 2.3, we studied the growth of an investment when simple interest is calculated. The scenario was a principal amount of $600 being invested at 5% simple interest. The goal of that lesson was to determine the interest earned and recalculate the value in the account. So here's what we did. We filled out this chart. So we invested the $600 at 5%. And so every year, our interest was the same because we were calculating simple interest. And then that amount of interest was added to our value in the account. So that's what increased to 630. Then the next year we earned another $30. So I added that to the 630 to get 660. The next year we earned another $30, so I added that to the 660 to get 690 and so on. And so you can see this is your running tally of the total of the accrued interest, the accumulated interest. Okay. And then you find the value in the account just by adding the interest earned to the whatever the previous principal was. Okay, so now we are pretty much going to do the same thing, except uh, we're going to see the benefit of what compound interest does. Okay, so example one, it says compute the amount of interest earned during the second year if the amount is 5% of both the principal amount of 600 and the 300. Okay, so the amount earned during the second year is what they want us to calculate. So they're telling us that the 5% is going to be on both the principal of the 600 and the $30 in interest. So that means I add those two together. So we're looking for 5% of the $630. So 5% of $630 is going to be $31.50. And so they want us to find the new ending value as well. So if we started with the $630 and the amount of interest that we earned on that was the 31.50, then that's going to give us $661.50 for a new amount at the end of year two. New amount at the end of year two. Okay. Now, let me pull the notes back from 2.3. So the end of year two, for simple interest, we had $660 in our account. Now at the end of year two, we have $661.50. Now that's not a make or break um, deal, right? Because it's just an extra $1.50. So big deal. Well, what you're going to see is that the longer you leave for compound interest, the longer that you leave your money in some kind of investment or an account, then the faster it's going to grow. You're not going to notice much change at the beginning, but then all of a sudden that thing's going to take off and then you're going to see a big difference. Okay. Now it says, we know from section 2.3, we can compute the amount of interest earned in 1 year using the formula I equals P times R. This is using T equals 1 in the formula I equals PRT. Use this formula with the principal of $630 to show that you get the same answer that you did in example 1. So they want us to use I equals the principal times rate times time. Okay, so with the new principal of 630, our rate is 5%, so that's 0.05, and then time is just going to be 1. Okay, So we're just going to number crunch. So taking 630 times 0.05 times 1, which, multiplying it by 1 doesn't do anything. And we got the amount of interest to be the $31.50. Okay. And that's what they wanted. They wanted us to show or to compute the amount of interest earned in 1 year using that formula. So there's the 3150, which is what we did. We just confirmed that. So we would add that to the 630. That was our principal to get the 661.50. Okay. So now we're going to fill out this chart just like we did in section 2.3. However, this is going to be different because now when we start, let's go ahead and start filling this out. So when we start, there's no interest earned. There's no accumulated interest. There's nothing to add that interest to. So we're going to start with the $600. Okay, so after the first year, we're going to calculate our interest. So it's 600 times our 0.05 times 1, which again, we don't need it. So that's $30. So we have accumulated $30 at the end of year 1. Now I add that 30 to the $600 that we invested. And now we have a new principal of $630. Okay, now this is where it's going to change from what we did in 2.3. Now I have a new principal. I'm going to take the $630, and this is what we just calculated. I'm going to multiply this by my interest rate of 0.05, which is going to give me $31.50. So now here's the $30 that we had from year 1 plus the $31.50 that we just earned. So now we have $61.50 that we have accrued in interest. So now I take the $31.50 and I'm going to add it to the $630 to my principal. And that's going to give us $661.50, just like we had calculated in examples 1 and 2. Okay. So now we're going to take the 661.50, multiply that by our interest rate. Okay. So here we go. So let's see, 661.50 times 0.05. So be careful because money. So this is going to be $33.08. Okay, now we have accumulated 30 from year 1. Then we had the 31.50 that we just accumulated, so we added that. So now I'm just going to add to the 61.50. I'm going to add the 33, 61.50 plus the amount of interest, $33.08. So now we have accrued $94.58 in interest. Okay. So I'm going to add my interest that I earned at the end of year 3, which was the 33.08, $33.08. I'm going to add my previous principal, which was the 661.50. So we're going to add those two together. $33.08 plus 661.50. That's 694.58. And then we have one more. So now we're going to start with 694.58. Calculate the amount of interest. So we're going to multiply that by 0.05. So 694.58 times 0.05. So that's be careful, $34.73. Okay, and then I'm going to add that to the previous interest that I had, which was a $94.58 plus $34.73, which gives us $129.31 that we have accrued in interest so far. Okay, so uh, our interest at the end of year 4 was $34.73 plus our previous uh, principal, which was the 694.58. Add those together. $34.73 plus $694.58, which gives us $729.31. Okay, now, again, I'm going to bring back our notes so that we can compare. So look at what we had. Uh-oh. Okay, I don't know what happened. All right, so look at what we had. So we started out with 600, then we had 630. Then you can see where it starts to increase. This is the compounding interest. This is simple interest. And look at the end of year 3, that's $4.58 more. And here, $9.31 more. Okay, so compound interest. Now, again, I told you at first, it's not going to be that big of a difference. Okay, and it's not that big of a difference. After 4 years, it's only a $9.31 difference. But you're going to see, we're going to work some problems in a little bit, and you're going to see a big change in what's going to happen. Okay. All right. Now let's get mathy now. Okay. So the value after 1 year. So what did we do? What could we do to make this a little bit easier? Well, what we did was we took our principal, which was the $600. And remember, don't forget our formula that we had been using. Okay. So if I use this formula, let me write it to the side. For the future value, if I use A equals P times 1 plus R times T. Now, really, I don't have to have the T because this is calculated at the end of every year. So time would only be, T would be 1. So really, this is what we're doing. Okay, so watch. So the principal would be the 600 times 1 plus our interest rate was 0.05. That gave us the $630 or that we would have at the end of the first year. Now, if I take this new principal, the $630, and I do this again, 1 plus 0.05, that's going to give me the 661.50. And then when I take that principal and I multiply that by 1 plus 0.05, 694.58. Okay. And then if I take the 694.58 and do that one more time, 729.31. We round up to 31 cents. Okay. So what we're doing is we started out with the 600 and then I multiplied that by 1 plus 0.05. Now that's going to give me, and again, that formula is coming from section 2.3, where T is 1. Okay, so this is going to tell me how much I have in my account after the first year. Now, for the second year, this is my new principal. Okay. So if this is my new principal, we're going to have the value after 1 year. Okay. So to find, remember, this is your new principal. Well, remember what we did in our calculation. I took that new principal, so I know that this is going to be 630. Okay. So I took that new principal and I multiplied it by 1 plus the rate. I did that again. Okay. Now, I'm just going to show you that what what gave us this calculation? Oh, I should have done this in red. Let me do this. So what gives us this calculation is this. Okay, so look, if I replace that with the value after the first year, I still am going to multiply that by 1 plus 0.05. Okay, well now look, I have 1 plus 600 times 1 plus 0.05 times 1 plus 0.05. Well, just like exponents, I told you we were going to get mathy. So if I have x times x times x times x times x, I can rewrite this as in exponential notation as x to the fifth. Okay. So if I have x times x, that would give me x squared because I have two of them that I'm multiplying together. Well, look, here's the 600, and we have two of these 1 plus 0.05s that we're multiplying together. So that means I can use exponential notation and turn that into 600 times 1 plus 0.05 squared. Now, that seems like an awful lot of work, but hold on, let's double check that. 600 times 1 plus 0.05, and then if I square it, remember, this should give us our value after 2 years. That's 661.50, and that is the amount of money that we would have after 2 years. After 2 years, there it is, 661.50. Okay. Now, example 4, what would the computation look like after 3 years? Well, this would mean I would want the value after 2 years times 1 plus 0.05 because this is going to be my new principal. And again, look at what we did. It's easier to show this to you. So look at what we did when we calculate our compound interest. You took your principal, got your new interest rate, and then we added it back. Then I took this principal, the new one, which is more because now I'm going to be earning interest on the previous principal plus my new interest that I'm going to earn. So now we took the 630, we got a new interest rate or interest amount, and I add that back to my previous principal, which made it bigger. Now I'm going to take this 661.50, calculate some more interest on a larger amount, and then I add that back to my principal, and then you just keep doing it over and over and over. So that's why our amount is getting larger and larger. Okay, so now remember this, let me use a different color here. So now the value after 2 years, we're going to use this. So 600 times 1 plus 0.05 quantity squared. And then I have this other 1 plus 0.05 that I'm going to multiply it with. Okay, so here's the 600. Now, look at this. I have two of these 1 plus 0.05s, and I'm going to multiply another one. Well, look, if I have if I have two of them, and then I'm going to multiply another, then that would give me x to the third, right? Okay, well, same thing. So here, this is going to give us 600 times 1 plus 0.05 raised to the third power. And that's how we would calculate how much we're going to have after year 3. So just for grins, let's calculate this. 600 times 1 plus 0.05 raised to the third power. Okay, we're going to have to round. That's 694.58. That's after year 3, $694.58. And look, after year 3, $694.58. Okay, so here's what we've got so far. To calculate the value after 1 year, that would just be 600 times 1 plus 0.05. To calculate the amount in our account after 2 years, that's going to be 600 times 1 plus 0.05 squared. And then to calculate the value after 3 years, that would be 1 plus 0.05 cubed. So now example 5 says, make a conjecture as to the value after 4 years and 5 years. I didn't catch this, period. Oops, period. Recall that conjecture is a math word for an educated guess. Okay, well, I hope you can see the pattern. So this is going to be 600 times 1 plus 0.05 raised to the fourth power because it's after 4 years. And this one would be raised to the fifth power. And all of this started from the same future value equation that we use for simple interest. The only difference is now, instead of multiplying it by however many years, you are raising it to some power. Okay. So that tells us that we now have this pattern that we can use. So make a conjecture as to the value after t years, where t represents any number of years. Okay, well, for any years, according to this scenario, we deposit our principal was $600 and we had an interest rate of 5% after t years. We just raise it to the power of t. So that means if I want to know how much am I going to have after 15 years, then I would take this, raise it to the 15th power. If I want to know after 25 years, I would take that and raise it to the 10th power or to 25. Okay. All right. So now, let's see. Hang on a second. All right. So now that brings us to our compounding interest formula. So compounding interest is going to be this one. A equals future value equals your principal times 1 plus the rate raised to the t power, where t is the number of years that you're going to invest your money. Okay? So now, and I'm putting this here just to remind you of what the future value for simple interest looks like. So if you compare this formula to this one, You can see it's still A equals P times 1 plus R, but this is where it changes. For simple interest, you multiply the number of years times the rate. But for compound interest, notice that's where we raise your 1 plus R to that power, okay? So simple interest, this is a linear function. A linear function. That means it's going to give us a graph of a linear equation. So it would look something like this. It would move in that direction. Okay. Compounding, your compound interest formula is going to be an exponential function because we have an exponent, that t. And these will look something like that. Okay, now remember what I said earlier for compound interest. Look at what this graph, look how this graph, look at what it does. So I told you at the beginning, you're not going to notice much of an increase. So when we start out, this would be at time 0. Then at year 1, it might get a little bit bigger. At year 2, it gets a little bit bigger. Year 3, a little bit bigger, however this is spaced out. But all of a sudden, this thing takes off. Then the amount of your investment gets big, after the longer that it has sat over time. Okay. So here's what we're going to do. Example 7. Use the formula for interest compounding annually to find the future value of $1,200 invested at 8.2% interest after 10, 20, 30, and 40 years. Then use a simple interest formula to find the future value. So in other words, we're going to use both of these formulas to fill this in. Okay, so here we go. Let's do simple interest first. Okay, so that we can see what we're looking at. So here they're telling us that T is going to be 10, T is 20, T is 30, and then T is 40. All right. They have given us, they want us to find the future value. We're investing $1,200. So P is 1,200. My interest rate, the 8.2%, is going to be 0.082. And then we have our different markers for time, 10, 20, 30, and 40. Okay, so I'm going to enter this in. Okay, so we have 1,200. Open your parentheses. 1 plus your rate is 0.082 times T, which is 10. And then close your parentheses. So P times 1 plus R times T. Okay, that gives us $2,184. Okay. Now, let's calculate this at 20. Okay, well, look, guys, we're going to be smart, work smarter, not harder. I'm not going to enter that stuff back in again. I'm going to arrow up till this is what I want, that calculation. I'm going to hit enter, and then I'm going to arrow over and change the 10 to a 20. Now we get 3168. Okay. I'm going to arrow up again, grab that calculation, change the 20 to a 30, because remember, we're calculating time when time is 10, 20, 30, and 40 years. So we change it to a 30. Now we get 4152. Okay. And then I'm going to go in, grab that one more time, change the 30 to a 40. And now we get 5136. Okay. Huh. Well, let's think about this for a second. If this is a linear function, because simple interest, I told you, was a linear function, then that means that it has to be increasing at a constant rate. So what is it increasing by? Well, this is easy to find. If I just take 51.36 and I subtract the 41.52, it increased by $984. So if I take 41.52 minus 31.68, it increased by $984. And then 31.68 minus 21.84, $984. Okay, so it did increase at a constant rate. Okay. All right, now let's calculate our compound amount. All right, so we're going to take this formula. So 1200 times 1 plus the rate, 0.05, close the parentheses, raise it to the 10th power, hit enter. Oh, wait, I'm sorry. Why did I do point? I did the wrong percentage in the percentage. Yeah, I don't know why. I guess I was just stuck in the 5% mode. Uh, so 1 plus 0.082 raised to the 10th power. Okay. So now we have to round. So 26.39 and 9 cents. 39 and 9 cents. Okay. And then again, I'm just going to back up, grab that calculation, arrow over, change the 10 to a 20. So this is 58, $5,803.99. $5,803.99. Okay. Now go back up, arrow over, change it to 30. $12,764.36. And then one last time, we're going to grab that and go over to 40. And we get $28,071.89. Okay. So, man, look at what I was telling you. The longer that you leave in your investment, the more it's going to make. Now compare it. You've got simple interest. After 40 years, simple interest, you're only going to get $5,136. But at the end of 40 years, compounded annually, you're going to get $28,000. Okay. That's almost 6 times as much after 40 years. Okay. I'm going to go ahead and save you. We did this in class, but we also used a different amount. But I'm going to save you the graph part here. All right. You're not going to have to graph that on the test anyways. All right. But I just wanted you to see it. So this thing does get exponentially large really quick. Or sorry, not quick, but it is, you'll see the difference compared to simple interest. It does uh, get large really fast. Okay. Actually, let me show you. I think it's important that you see this. So let's take, this was 1200 times 1 plus 0.082x. And then let me enter the other one in. Okay. And then I'm going to compare, I'm also going to put in our exponential. So that one looks like raised to the x power. Okay. Now let's see, zoom. Let's set it to standard. Oh, why do I have that in there? Shoot. This is from my college algebra class. Okay, well, sorry guys. I was going to show you the difference between both of these graphs. Okay, so I went ahead and I paused the video real quick and I went ahead and fixed uh, the window. So this is your now it's not a clean graph because I didn't spend too much time adjusting the window size for each graph. But you can see that the blue line would represents your simple interest uh, formula, and you see it's a line. So that's linear. And here's your exponential. Over time, you can see that it doesn't change much. If you were to zoom in, well, here it is because even after 10 years, we're seeing well, after 10 years, the difference is $500. Well, around 500, right? Or 400, something like that. Okay, between these two amounts. So there is going to be a little bit of a difference. But the longer that amount is left in for compounding, you can see how at first the change isn't too significant, but then all of a sudden, boom, it picks up and then your amount will increase. Okay. So again, compound is going to be your exponential. It's the red one. It's that curve. And then simple interest is the linear. Okay. All right. I just wanted you to see that. All right. Now let's talk about uh, let's dig in a little bit deeper to compound interest. So what we've done so far is we had calculated our compounding uh, period to be after 1 year. We compounded it annually. Now, that's not always the case. So far we have calculated interest amounts that have been calculated compounded yearly. But what happens if our compounding period is something other than yearly, such as quarterly, monthly, daily, bi-monthly, semi-annually? It can change. Okay, so let's say that the interest is being compounded 4 times per year, which means that would be compounded quarterly. Okay, using our previous scenario with the principal of $600 and the interest rate of 5%, the banker would not calculate 5% 4 times because if he does, then that's way too much. Okay, so that would correspond to a much higher rate than the 5% promised. Instead, we divide the interest rate by 4 and pay 1.25% every 3 months. So quarterly, that means you would divide up your year into quarters. So if you divide 12 by 4, that's 3. So every 3 months, your compounding period, uh, your interest would be crunched. Okay. So the first calculation after 3 months, so what is that going to look like? Well, we would take, so the future value, it would be the 600 that we invested times 1 plus. Now, if we have our interest rate at 5%, we are going to divide that interest rate by 4 because it's compounded quarterly. Okay. And then that would be the first 3 months. Okay. Now, after 6 months, write a calculation that describes the future value using the same idea for the above example. So how many times would the interest be calculated after 6 months? Okay, so uh, we're dividing our rate by 4. So for the first 3 months, that's 1 time. For the second 3 months, that would be a total of 6 months. So that would mean that our exponent would change. And that would be having to raise this to the second power because that would be running into its second cycle for determining how much interest it's going to pay out. Okay. So by the time the first year is up, the interest would have been calculated how many times? So remember, it's every 3 months. So January, February, March, that's one. April, May, June, that's two. July, August, September, that's three. October, November, December, that's four. Okay, so it would be calculated four times. So the total exponent on the parentheses in our future value would be four, which is the number of times per year that interest has been compounded times the number of years that have passed. Okay, so if the interest is compounded monthly after 5 years, it would be compounded how many times? Okay, well, they told you that your exponent is going to be the compounding period times the number of years. So if this is compounded monthly, then that means 12 times. And then for how many years? 5. So 12 times 5, that's going to be 60. So 60 times. Okay. If the interest is compounded n times per year after t years, then it would be compounded n times t times. Meaning, let's say that this was compounded daily for 2 years. Okay. So if I said daily, compounded daily for 2 years, well, in in a year, how many days are there? So there's 365. So that would be n times the number of years, which is 2. And you multiply that out. So 365 times 2. I have no idea why this thing keeps uh, doing this. Sorry, wrong. Go away. Okay. All right. So 365 times 2, 0, 12, 3. So 730. This would be 730 times. Okay. So you just multiply those two together. All right. Now adapt your answer into a formula for calculating the future value of $600 invested at 5% interest if the interest is compounded n times per year for t years. Okay. So here's what they're saying. They want you to write that formula. Okay, so for future value, it would be your principal times 1 plus your interest rate, which is 5%, compounded n times per t years. Okay, and that's what it would look like. Okay, so here's the general formula now. So our compounding interest formula would be P times 1 plus R divided by N, your rate divided by the compounding period, raised to the compounding period times T power. Okay. Now, if it was yearly, T would just be 1, so then we wouldn't need it. Oh, I'm sorry. I'm sorry. I take that back. What I meant to say, if it was compounded yearly, the N would not be there. Then we're back to what we had started with because we're just doing it every year. Okay. But here's what you got to keep in mind. If you look at the bottom, I've given you some compounding periods that you need to be very familiar with. Daily is 365. You would use these numbers. Weekly is 52 weeks in a year. Monthly, 12. Quarterly, 4 times a year. Bi-monthly is every 2 months. So that means 6 times a year. And then semi-annually would be twice a year. Okay. Now remember your compounding periods, sorry, there's nothing to remember because I haven't told you yet. Your compounding period will be given to you in the problem. You have to look for it. but it's very obvious. It's like clearly stated. It would say, the interest rate is, 8.3% compounded quarterly. So it would be very obvious, and so would the length of time. That would be very obviously in the problem as well. Okay. All right. So here we go. So it says calculate the future value of the account given that you invest $945 at 7.45% interest compounded quarterly for 10 years. And the same investment, interest, and time compounded annually, which is the better result. So we're going to do two of them. All right. So first, we're going to look when this is compounded quarterly. Okay. So off to the side, here's what I'm going to do. And it's always, again, you always want to identify your variables. So P, our principal, is going to be $945. Actually, we're going to have two calculations here. So well, I'll just change what needs to be changed uh, color-wise in a minute. So our principal is $945. Our rate is going to be 0.0475. And then our T time is going to be 10 years. Okay, so here's our formula. Now, compounded quarterly, this means that little n is going to be 4. All right? Okay, so here's our formula. A equals P times 1 plus R over N raised to the N times T power. Okay, so I'm going to plug these numbers in, and then I'm going to do one number crunch in my calculator and get our answer. 0.0475 divided by N, which is 4, all raised to the 4 times T power. T is 10. Okay, so we're going to get a future value is approximately, because I know this is not going to be a nice number. Okay, so 945 times 1 plus 0.0475. Okay. Divided by 4, close the parentheses, raise it. Now, if you have an 83 and you raise it, you have a TI 83. And when you get to this step, open your parentheses and type in 4 times 10 and then close your parentheses. That will make sure that all of that calculation is done right. And even if you don't, if you have, an 83 plus or an 84 or an 84 plus, you can still do the same thing and it'll ensure that you're going to get the right answer. Okay, so this is approximately $1,515.33. Okay, so that's what the future value would be compounded quarterly. All right, now they want to know what is it going to be when it's compounded annually. If it's compounded annually, then n is just going to be 1. Okay, so again, we have the same PRT. So 945 times 1 plus our rate, 0.0475. And I'm going to go ahead, even though we're dividing this by 1, I'm still going to plug this in so that you can see where this number is going to go in your calculations. Okay, T is 10. All right. And then A is going to be approximately how much? All right, so here we go. So 945 open parentheses 1 plus. Now, I'm just going to enter 0.0475. If I divide it by 1, it's still 0.0475, right? And then we're going to raise that to the 1 times 10 is just 10 power. And you can see, oh, that's 5 cents. Okay, so there you go. So the future value compounded quarterly is $1,515.33, and compounded annually is $1,503.05. So obviously, the compounded quarterly option is the better. So we want to say this is the better one. Compound quarterly is the better option. Okay. All right. There we go. Okay. Example 9. Find the interest on an investment of $75,000 that pays 4.5% compounded weekly for 8 years. Oh, man. Well, remember your formula. Here it is. That's your formula for compounded interest using compounded interest. And notice I don't have the option to solve for the interest alone. So I don't have a choice but to do this, but somehow I'm supposed to find what my interest is going to be. Well, again, hopefully you haven't forgotten, we've already solved problems like this. Okay, so first let's identify uh, our variables. So our principal, our investment is going to be $75,000. Our interest rate is going to be 0.045. Our T is going to be 8 years. And our compounding period, it's compounded weekly. So little n, well, how many weeks are there in a year? There are 52 weeks in a year. Okay, so that's what I need. So I have to find the future value. So A equals P times 1 plus R over N raised to the N times T power. All right. So A equals 75,000 times 1 plus 0.0475 divided by 52 raised to the 52 times 8 power. All right. So here we go. So in one calculation, we're going to crunch this out. 75,000 times 1 plus 0.0. Oh, look at me. I looked up for just a second. 0.045. Okay. Divided by 52. Close your parentheses. Raise it to the 52 times 8 power. And boom. There you go. Okay. All right. So that means, oh, sorry. That's our future value is $107,482.97. Okay. But that's not what they want. They want to know what is the interest. Well, we invested $75,000 and the future value at the end of the 8 years, my $75,000 that I invested is going to get me $107,482.97. So what made my $75,000 increase to this amount that's over $107,000? So the difference is going to be the interest that was earned. Okay, so all I have to do to find the interest is take your future value and subtract the principal from it. So the 107, 482 and 97 cents minus the $75,000. Okay, so I'm just going to subtract 75,000. And so the difference is going to be $32,482.97. And that's the interest that was earned on that principal of $75,000. Okay. All right. One last problem, and it's another compounding formula, but this one is different. So you use the compounding formula, this A times P, the P times 1 plus R over N raised to the N times T. When they give you compounded monthly, daily, weekly, blah, blah, blah. Okay. Whatever they say it is, you have numbers that you can plug in for N. Okay. Now, if they tell you that it's compounded continuously, this is a completely different formula. When they tell you continuously, you're going to use the formula that has the E in it. P times E raised to the R times T power. Okay. So, example 10, calculate the future value of an investment of $40,000 with 6.9% interest compounded continuously for 25 years after it's started. Okay, so A equals P times E raised to the R times T power. So here's the P. Your rate is going to be 0.069. T is 25. And then notice that I don't have a number to plug in for N. And that's because this is compounded continuously. Okay, so we're just going to plug in. But look, all I need is a P, an R, and a T, and I have the P, the R, and the T. So the future value is 40,000 times E raised to the 0.069 times 25 power. Okay, now let me show you how to get to the E button. E is an irrational number, and it goes on and on and on and on and on, just like pi. If I evaluate pi, we don't say that pi equals 3.14. No, we say pi is approximately 3.14. Okay. So with E, E is approximately, I think it's 2.71, but here's your E button. Notice it's with the LN button. It's right here, and right underneath the log. Okay, the LN button. This is how you're going to get it. So you're going to press second, and then if I press the LN button, then I get E, and then it shoots up that little exponent. So I'm just going to say my exponent is 1, just so that we can see what the value of E is. Yeah, 2.72. Sorry, approximately 2.72. Okay, but it's a number. It's an irrational number. It goes as a decimal. It goes on and on and on and on and on, and it never stops, just like pi. Okay, now here's how we use it. So we're going to crunch in 40,000 times E. So that's second ln. So I get my E, and then the exponent is going to be 0.069 times 25. Again, TI-83 users. Once that exponent block pops up, open your parentheses and type everything that you need to type in for your exponent. and then close it. Okay. All right. And there's our amount. So our future value is approximately $224,500.84. $40,000 investment compounded continuously for 25 years at an interest rate of 6.9% will get you approximately $224,500.84. Okay. All right. That's it for this section, guys. Let me know if you have any questions.